Yeah. Let's see if that works. Okay, so that's the recording in progress. So fantastic. Okay, well, hi everyone. My name is Lee Patrick, and I'm a sort of new member of the Comisión de Seminarios here at the CAB, and it's my absolute pleasure to introduce Sergio Ioppolo today to talk to us about astrochemistry. Now, Sergio is currently a professor in the Department of Physics and Astronomy at Aarhus University in Denmark, and he's also a PI or possibly the PI of INTERCAT. API of INTERCAT. Yeah. Now, sort of throughout Sergio's career, he's done really quite a grand European tour. So if I miss anywhere, Sergio, please, let me know.
No worries.
He started his career as an undergrad at Catania University in Italy, and then went on to do a PhD at Leiden University. In 2011, Sergio was awarded a Niels Stenson Fellowship and jointly a Marie Skłodowska-Curie Fellowship, international fellowship, which he took to Caltech. Now, after some years at Caltech, he was awarded a Royal Society Fellowship, which he took to the Open University in the UK. And then in 2015, he moved that fellowship to Queen Mary's University. And earlier this year, Sergio took the moved to Aarhus University in Denmark, where he's started as an associate professor. So with that, Sergio, I'll kind of hand over to you and let you start sharing your screen.
Yeah.
And and let you provide this great.
Thank you so much, Lee, for the introduction, a nice introduction. Okay. Good afternoon, everybody. It's my pleasure to give this seminar to you, although unfortunately it's online. Hopefully next time I'm going to be able to visit. All right, so I'm going to talk about some of the work that I have done recently at some of the European larger facilities that we have available at the moment that are interested in laboratory ice astrochemistry. But before that, I'm going to give you a little bit of an introduction. Probably you all know that our universe is molecular in its nature, with more than 300 species unambiguously identified in the gas phase, and just a few of them identified in the solid phase. As you can see here on the left side, I hope you can see my cursor. You see the relative abundance of species in the solid phase that are molecules that were deposited from the gas phase onto dust grains in the denser regions of the interstellar medium. And the most abundant one is water that is actually formed on these grains. And then we have CO2, CO, methanol, ammonia, methane, and a few more that are not mentioned in this graph here. If we look at the composition of molecules, of these 300 molecules, we have inorganic species, we have organic species, we have small species, we have also large species such as like C60 or so. And the ones that are quite interesting to me and probably many people there in Madrid are the so-called complex organic molecules that are complex from an astrochemical point of view, in a sense that we call COMs all species that have at least 6 or more atoms that contain carbon and oxygen and hydrogen. So these molecules that are complex are like molecules like methylformate, acetic acid, glycolidide. Those are all considered complex organic molecules, and those are readily observed in hot cores and hot corinos, and they could form through gas phase reactions in these environments. There is quite some higher temperature there, so above 100 Kelvin or so. They could also come from the grains by thermal desorption in these regions as well. But more recently, we also had the identification of COMs in colder, denser environments, such as prestellar cores. And this was a bit surprising, because if these molecules are formed in the gas phase, then we might not know all the possible reaction pathways there, because many of those gas phase reaction pathways under these conditions are not really efficient. Or if they are formed in the solid phase on top of dust grains, then we don't know how they desorb from the grain to the gas. And citing one of the most recent papers that Victor and Izaskun and Laura and others were involved in, now we also are able to detect astrobiologically relevant species, such as ethanolamine and in space conditions in the gas phase. So the question that people like me that work in laboratories have is, if we have all these molecules there in space, where do they actually form? So under what kind of conditions do they form? And how do they form? Do they form in the gas phase? Do they form in the solid phase? Most likely it's going to be a combination of the two. But what is the most effective and efficient mechanism that lead to the formation of these species as a function of the physical conditions that you have in the interstellar medium, which are like a large variety of those. And speaking about that and looking at the evolution of clouds from prestellar cores to solar-like systems, can comets survive the formation of stars and planets? Those are all interesting questions that are not, and they're simple questions, but they're not easy to answer. And if we assume that molecules such as organic species can be formed on the surface of ice grains, can we detect those species? As I just mentioned, only few molecules have been identified on the surface of dust grains, but can we detect complex organic ones? And if they are formed in the solid phase, how do they actually form there? If you look at this scheme that we have here on the right side, there is depicted all the different major mechanisms that lead to formation of molecules. We have here on the top right side, atom and radical addition reactions. Basically, we have atoms and molecules and radicals that from the gas phase freeze out on top of the grains. And there they can, the grain can act as a third body and can catalytic surface and help the recombination of those pieces into larger molecules. That's the way we know that, for instance, methanol form and up to molecules as large as glycine have been proven to be formed through this kind of mechanism. And we also have thermal chemistry that is induced by the thermal heating of the grain and the ice that increases the diffusion of species within the ice, and therefore the mobility of the molecules, that they can find each other and react. This is something that could happen just before the hot core stage, before all the species come off the ice. So there would be even more chemistry in these conditions. And then we also should include and consider energetic processing, such as the effect of photons, UV photons, electrons, cosmic rays. They can all induce chemistry by breaking the existing bonds of molecules within the ice and injecting enough energy for them to diffuse and find each other and recombine into either smaller species or larger ones. And then finally, also something that more recently people are looking at is like collisions and shocks events that can also induce chemistry and restructuring of the ice. So if we think about why we haven't been able to identify complex organic species in the solid phase, at least unambiguously, one of, or few of the reasons why that's the case is because the way we observe molecules in the solid phase in space is with a source as a background. There could be a background star, a field star, or a protostar that is forming, that is behind the cloud where all this gas and ice is. And then there is the observer, as is depicted here on the left side. Also, so therefore we need to have a source at the back. We cannot look at ices everywhere in any direction. The other thing is that we are looking at ices in the interstellar medium in the mid-infrared. And in these regions, there is a lot of telluric absorption from Earth. So unless you're looking at specific windows that are available, most of it is covered by water absorption in our atmosphere. So therefore, we need the space missions for that. And there have been a few of those, like ISO or Spitzer, and as I'm going to mention very soon, JWST now. But those have been so far quite scarce, rare, and the database of ices in space is quite limited at the moment. What we see here on the right side is the comparison between a field star here at the bottom in blue compared to a low mass star in red and a high mass star in black. So if we compare these existing spectra, that those are from ISO, I believe, and actually these are probably a composite of different observations as well, maybe even from the ground in the region of the CO and CO2. And you can see that when you have a background star, so it's like a quiescent region, then you see the spectrum of the star at the back as a background, and on that you see overimposed some negative peaks. So all these negative bands, they are pointing down. Those are absorption that are due to the silicates, mostly this band here, as well as the ice. And here you see that you have, for instance, methane, and this is like here is water, as you can see. And if you compare this spectrum with the one of low mass star and especially the high mass star, then you see that the larger, the more massive the object is, the more perhaps evolved the object is, the more complex this absorption look like. And indeed, here in the high mass star, it looks like there are some question marks on some of these complex organic species that could contribute to the bands that we see in the spectrum. Unfortunately, as I was saying, we have sparse data, and the resolution, the spectral resolution is not always optimal, especially in the case of Spitzer, or we don't have the right sensitivity in the case of ISO. So what we do from the laboratory is to provide all the possible spectra that we can study of all these molecules, and we can compare with observations. That's how we get to know which kind of molecules there might be on these observations, as you can see here on this plot on the left. Dashed line is a laboratory spectrum of water, and the other one is the observational spectrum. And you can see that the water overlaps very nicely with this spectrum here. And we can do it with simple species, we can do it with complex species. But as you can see on the right side of this, these are laboratory data. If you look at this already small sample of species, some of these bands start overlapping with each other. And that's what is called spectral confusion. So different molecules, especially the most complex one that we can think about to trying to identify in ices in space, might have the same kind of functional groups, and therefore will have the similar absorption in the infrared. Therefore, you will not know which exact molecule gives you that absorption, but you mostly will be able to identify a family of molecules that have the same kind of vibrations that could contribute to that specific absorption in the observations. This is another issue that we have. But at the moment, we are all quite excited because we have the James Webb Telescope that has started working for us and collecting data of ices in space. In the mid-infrared, so we have, and in the near-infrared, we have here the image of the NIRCam here compared to Hubble. In the mid-infrared, that shows that now we will have enough spectral resolution and spatial resolution and sensitivity to actually obtain a large variety of observations across many different sources that will help us constrain the presence of complex organic species in ices in space. And this is the very first paper that was out a few weeks ago on one of source that was observed with MIRI in the mid-infrared. And here you can see already the quite nice resolution that Spitzer can have. And we already, in this case, have perhaps observed some of these complex organic species, because all these little weak bumps are actually real absorptions. And there are, of course, still some unknowns at the moment. These are the very preliminary spectra, but much more is going to come up very soon. And for instance, I am personally involved in the Ice Age consortium that with Melissa McClare as a PI and co-PIs is Edwin Bugert and Harold Linards. And here the first data that we actually submitted to Nature Astronomy were on two sources at the highest extinction that we ever observed at 60 and 95, showing the absorption of several different molecules. As you can see here, we have the absorption due to water, but we also can see clearly CO2, CO, methanol, methane, ammonia. So all those that were already identified before, but we have some newcomers here. So we have, for instance, something that we were always puzzled about was the OH dangling, so a surface mode of water ice that we always saw that in our laboratory spectra, but we never observed in space. Apparently here looks like we have the dangling mode at around 2.75 microns, which is very interesting to see it in this at these extinctions. Perhaps is due to the fact that here the ice is a little bit thicker, so there is a little bit more scope for porous ice to be formed. And the other thing that we can see here is the OTN minus, OTS, and these are now clearly observed. And we also can see some of the isotopes. So we have now clear signals from 13CO2, 13CO. And as you can see here now, with the resolution that we have at the moment, we could already fit the 13 CO2, not just the regular, the natural 12 CO2, but the 13 CO2, so the weak bands, with a series of laboratory data. And what we can see here, and it's something that I want to point out, is that we fit the profile of the observations not only with pure CO2 ice deposited at 10 Kelvin and acquired in the laboratories, but in order to fit this asymmetric profile, we need CO2 in different environments. We had to use a mixture of CO2 with water, CO2 with CO, CO2 with methanol. Now, how does CO2 form in space? And this was one of the questions that I was mentioning before. If we think about CO2, a simple molecule still, but the formation is quite already a complex deal, because when you have the early stages of ice formation, you are in a water-rich ice. So water has been formed in this stage of ice evolution during the star formation. And in this environment, you have the surface formation of water, as I was telling you before, through atom addition reactions. So the addition of oxygen and hydrogen that lead eventually to the formation of water. And then in parallel, you have the hydrogenation of CO. CO comes from the gas phase and eventually will freeze dramatically, creating a layer on top of the water ice. But at this stage, it might still deposit because the temperature is already 10 Kelvin or so. So some CO could get deposited, could get hydrogenated. And if it's in this water-rich environment, could also lead to the formation of the OCO radical, so the HOCO radical, that could be directly dissociated in CO2 or further hydrogenated to CO2. So CO2 comes from surface reactions in a water-rich environment. So it makes sense to have a mixture of CO2 and water in our observations. So it's not just something that we came up qualitatively, but it's actually there is a reason for that. But if you also think about all the other mechanisms that I mentioned before, the energetic ones, then even if you have just pure CO in a later stages or CO in a water-rich environment, you do form CO2 through the irradiation of CO. So here you see an experiment of ion irradiation of CO, pure CO, and the formation of CO2. And this is just an example. So energetic processing like photolysis, cosmic rays irradiation, electron irradiation of carbonaceous species can lead to the formation of CO2. So that means that CO2 is embedded in different environments in interstellar ices, and this needs to be taken into account. And this is something that we already see observationally. So we can prove it with experiments, and we have the observational confirmation that the profile can only be fitted when we consider different environments. But also, on the other hand, we can use that as a tool. So if we know the profile of CO2, we can actually also use that as an indicator of the temperature history of a certain source. So, for instance, here, this is already an old work from Klaus Pontoppidan. He fitted with just deposited ices the profile of the bending mode of CO2. The one I was showing you before was the stretching mode. Now we are at 15 microns. And you can see that the profile across different sources is dramatically different. If CO2 is diluted in other molecules, present a single peak. When it's pure, I should also say crystalline, as a splitting, this peak becomes a double peak. And there is also a shoulder here on this side. This work was done just by depositing ices in the laboratory and comparing. So that's something that that has been done in Leiden and with the LIDA database for decades at this point. But what I did also years or so ago was to produce CO2 through ion irradiation of ices that contain carbon. So, for instance, mixtures of, well, actually a layer of water on top of carbonaceous grains, or pure methanol here, or just pure CO, and irradiated with different ions at different energies at around also different temperatures to see whether the profile of the CO2 band would change as a function of the environment. And we were able also to reproduce the profile of field stars, so quiescent clouds, as well as ALMA star, where the profile looks much more complex. There is a splitting again, and the shoulder was actually well fitted by the presence of methanol in the ice. But, as you can imagine, the fact that CO2 has so many different is so sensitive to the environment, and so the spectra looks so different. Then what is the actual spectrum of amorphous CO2 according to the laboratories across the world? So if you look at this plot here, there seems not to be an agreement of what a pure amorphous CO2 is spectroscopically in the mid-infrared. You see the spectra acquired of what is nominally called pure CO2 in different laboratories across the world. And you see that some of them have a single peak for the stretching, some others have a double peak. In the bending mode, some of them have like a strong splitting and others a little less. So there is not really an agreement. And this was pointed out by the Perry-Girakines and Reggie Hudson in this paper in 2015. And they came up with their own spectra showing the crystalline ice that shows a nice narrow single peak for the stretching mode and a narrow double peak for the bending mode. And the amorphous one that they deposited very slowly, very gently, presented single peaks that were quite asymmetric. So that seems to be a nice end of the story, but actually it's not, because then other groups also looked again at their data and trying to do more carefully the same kind of deposition, and still saw the splitting at the bending mode. And so for the crystalline ice here, there is quite a good agreement. If before you saw the peaks pointing up and now you see the peaks pointing down, that's just because some people plot them in absorption, others they plot them in transmission. So it's just that. But the point that Giuseppe Boratta and Elisabetta Palumbo had is that if you just have a little bit of water, there could be just like a water contamination in your experiment that you don't see because it's such a small fraction over all your full ice. CO2 is so sensitive that actually the splitting disappears in the bending mode, as is shown here in this plot here of the bending mode. So if you deposit this mixture with just a teeny tiny fraction of water in it, the splitting mode, the two bands disappear and become what Reggie Hudson and Perry-Girakines showed. So it is likely that actually also in their experiment there was a little bit of contamination. Therefore, it is key to do experiment under as much controlled conditions as possible, knowing exactly all your metadata, which means all the conditions around your experiment, in order to be able to be reproducible, and not just within your own lab, but also with in other labs. If you look also at other techniques, here we see that, for instance, tunneling emission microscopy shows that if you deposit CO2 on amorphous water ice, the image looks quite scattered, and the CO2 should be the darker dots, so they look like quite spread around on more or less homogeneously. But already when you warm up the ice around 50 Kelvin or 60 Kelvin, you see that that the CO2 is segregating in the darker spots, and they interpreted that as already a sign of crystallinity of the ice. So this is an indication that perhaps also CO2 is very mobile, even a lower temperature than what is expected, because its desorption should be around 70, 80 Kelvin. So you would expect the crystallization just before that, but actually you have crystallization perhaps even at 40 Kelvin or so. And so the diffusion or the mobility of CO2, even at lower temperature, might make it even harder for laboratory studies to actually get a nice layer deposited of amorphous CO2 ice. And that's where all this laboratory work at our larger facilities can help, because here we can use different tools that can be unique of the specific facilities to help us address specific questions that we have. So the CO2 was just an example to give you an idea of how complex experiments could be, even when you are studying simple species, so very small molecules, and not even talking about complex organic ones. And here today, I'm going to talk a little bit about the work of some of my PhD students and postdocs that worked at these different facilities. So the first one that I want to mention is the Felix free electron laser facilities in the Radboud University in Nijmegen in the Netherlands. So if you see here in Europe, here where the star is the Netherlands. And there I built an ultra-high vacuum chamber called LISA, this lab ice surface astrophysics. That is just an ultra-high vacuum system that can go down to 10 to the minus 10 millibars. So under vacuum conditions, we have a substrate at the center where we can deposit ices through background deposition, which means that the ice is deposited not directionally, but from anywhere. And we have a infrared spectrometer to do infrared spectroscopy, and a quadrupole mass spectrometer to look at the species coming off the ice. We can also manipulate the substrate, and we have an electron gun as well if you want to do chemistry. What we do there that is unique of the facility is that we use this laser that has a wide tunability. It's a monochromatic or nearly monochromatic laser, so we can change the frequency of the laser continuously throughout the mid-infrared and the far infrared terahertz range. This laser is quite intense and has short pulses. So in principle, we can look at pump probe experiments as well. What we have done there so far is to have this experiment also open to the space science community, and others can also apply for beam time. There is actually a call now with deadline on the 15th of November. If you're interested, just let me know. There we look at the effect of infrared radiation on interstellar relevant ices and what that causes to the ice, whether that induces chemistry or just physical changes in the ice. That's something that we are tackling. And the analog of what we do in these laboratory experiments to space is that there is a lot of infrared radiation in space as well. It can go through dense clouds, and that's because some of these molecules, of course, absorb some of the light, but most of this light goes through. So these interstellar ice grains are constantly exposed to infrared radiation. And there is also the effect of the fact that because molecules can absorb this energy vibrationally, so then when you have a cosmic rays impinging on an ice, this will cause some sort of heating around in the area where the projectile goes through. And this sort of heating could be quite localized. And these irradiations are also quite localized, I will show you in a minute. So they could also simulate the effect of the heating effect of cosmic rays, as well as the heating effect of collisions when you have coagulation of grains and shocks when you have shocks in space. So all these sort of thermal effects we can reproduce because we are injecting sort of infrared, that means the thermal energy in your system. And that can cause changes in your eyes, so phase change from amorphous to crystalline. That also can induce diffusion of molecules, as I was also mentioning briefly before, and perhaps desorption of species. And that could be a nice way to understand why we have complex organic species in places that are actually quite cold, like prestellar cores, but there is a lot of infrared radiation. If that is gentle enough to kick off some of these species into the gas phase, perhaps that is a nice and effective mechanism, as opposed as to the UV photolysis or photodesorption in the UV that looks like it's going to fragment all the complex species. And finally, we are also looking at some larger species such as pHs in ices and what their interaction with the infrared light. So just to show you an example, here we have the position of water ice, and we can irradiate selectively all the different modes of water ice. I mentioned before the wedge dangling mode, which, if you don't know, is basically the fact that some of these molecules might have part of them sticking out in the vacuum, so at the surface of your ice material. So you might have an hydrogen sticking out and vibrating in the vacuum here, or like this, or like that, and so on. And then we have also the bulk mode, or the stretching mode of water ice that we can excite. We can also excite the bending mode here, or the vibrational mode, the combination mode, or we can also do irradiation of resonance, so in places where there is no absorption, and see the effect. What we look at is if you have here the stretching mode of water ice, so it's this band here, is a zoom in on this area. The changes that we see are quite small, and so what we do is we acquire a spectrum before and after irradiation with the infrared beam, and then we do the difference of the two. So if nothing happens, nothing has changed in the ice, you will see basically a flat line, as is the case when there is no absorption, the gray one here, which is this irradiation there. But when you irradiate on resonance, so when actually the ice at the frequency where the ice is absorbing vibrationally, then you actually see some changes in the ice. Before and after irradiation, you see some negative peaks, some positive peaks. So something is decreasing, other things are increasing in the strength of these vibrations. And what it is basically that we could fit these changes with spectra acquired of water ice at different temperature to see whether this is a thermal effect. So whether we are restructuring our ice. And what it looks like is that actually we are increasing the degree of crystallinity of the ice, because here you see the red one dashed line is a more crystalline ice, and that fits nicely in this profile here as an added spectrum, while the other one, light blue, is negative, which is the amorphous ice, which means we are reducing the quantity of amorphous ice in our samples. And because of the fact that the infrared beam is smaller compared to the laser beam is smaller compared to the FTIR, so the spectrometer beam, that means that we are monitoring mostly ice that was not processed. Therefore, this effect seems small relative to our spectra. But if you scale that down, then it looks like that 90% of the exposed ice actually restructured. And you can think, okay, but this is a powerful laser. You probably are doing multi-photon processing of the ice. Well, as far as we can tell, and also from the simulations that Herma Kappen is doing, it doesn't look like it's a multi-photon process. It's a single photon process. We can see that is nicely linearly scaled with the power, the effect that we see experimentally. And therefore, if it's a single photon process, it is interstellar relevant. So if we go back to CO2 and we deposit CO2 at low temperature at 20 Kelvin or at higher temperature 75, then we should definitely have an ice that is more amorphous and another that's definitely crystalline. And we can expose the two of them to the infrared radiation and see the changes that we have in the ice and what happens to the ice when we do that. We can do it as a function of frequency and irradiate the stretching mode here of the amorphous ice in different spots. So here around the peak, the main peak, or at the wing, as well as doing the same for the bending mode at the 15 microns. And you can see that when we irradiate the main peak, we do see changes in our ices. We have some peaks that are going up, others are things that are going down for the stretching and the bending mode. And when we irradiate the wing here of the stretching mode, we only see negative peaks. So now negative peaks could also mean desorption, because it's like something that is leaving the ice. There is less absorption overall. But when you have a positive peak in this case, it could be crystallization. It could also be that the peak is just shifting. And so then a closer look at that needs to be done. When you look at the bending mode, though, the radiation, we only see negative peaks here, which probably is indicating us that all these effects are really frequency dependent, so are vibrational dependent. So whether we are exciting a specific vibrational mode or another, the effect could be different. And in this case, specifically seems to be desorption, the most important thing. Unfortunately, our QMS was not functioning very well, so we only have infrared data and not mass spectrometry data. But we are improving that, as I will show you in a minute. So if we look at the different spectra, again, with a warm component and a cold component, again, the cold component is negative, so it's going down in quantitatively, and the warm component is increasing up. So there is, again, the indication that the ice was restructuring from a more amorphous structure into a more ordered-like structure. But when we irradiate the bending mode, we can clearly see that we cannot do this kind of fit. The fit is not satisfactory at all, indicating that we likely have some desorption of the ice there. If we do the same thing for the crystalline ice, now, regardless of what frequency we use, the effect is very similar in all these cases, indicating that we are not restructuring an ice that is already crystalline. So we were going toward a more ordered ice, and in this case, it's not possible anymore. So the only thing that could be possible is perhaps some desorption, and indeed we see when we do the different spectra that there is still more negative peaks than overall that we can fit. So that is an indication that perhaps we have desorption there too. And so what happened when we mix water and CO2? In this case, we can irradiate the water modes and we can irradiate the CO2 modes and see whether there is any difference. So one of the questions is like, can all this vibrational energy be transferred in any case to the OH network, so into the water molecules, and be dissipated effectively with the water network or not? We did this sort of experiments of these mixtures, and Diane has been working on to repeating this as a function of different mixing ratios. I'm just showing you one case here, and you can see that the results are different as a function of the frequency that we have. So this is a frequency-dependent effect that we have, and is most strong when we irradiate the stretching mode of water ice, and it gives you more or less the same effect that we saw for pure water ice. And with the larger negative peak for the CO2, which probably means that some of the CO2 molecules are kicked out, even when we irradiate only the water ice. So when we do our fitting procedure, we can nicely fit the profile both of CO2 and water when we try to fit the 3 micron irradiation, so the irradiation of the water band. But this is not the case when we try to do the same for the irradiation of the CO2, indicating that this is most likely not a global warming effect, but is a local effect that only affects certain molecules that have a certain orientation within each other, and that therefore the energy is not distributed overall throughout the lattice of the ice, but only specifically to certain molecules. And then in the future, we are going to get a new quadrupole mass spectrometer that can allow us to do time resolution experiments, and hopefully will constrain the photo desorption in the infrared. So stay tuned for that. Now, quickly, I'm going to mention some other facilities, for instance, such as the Atomki one in Hungary, where we have already two end stations that can simulate ion irradiation of interstellar and solar system ices. So here you have the ion accelerator, and one of our stations is here at the end. And here you see the end station and Duncan, the PhD student working there. There were calls here for a beam time, even recently. And I know that one of the group from Madrid already applied. Belen Mate, Victor Herrero also applied for beam time there. So hopefully we are going to get some beam time together. And the chamber is an ultra vacuum chamber again. In this case, we have the ion beam coming from one side, the infrared from the other side. We are doing transmission spectroscopy here. And we also have an electron gun, as I will show you before, later. And the unique capability of this sample is that we have 4 windows that we can use to do systematic work. So we can use the Tandetron facility to use different ions or investigate different energies within a single ice deposition. So at having exactly the same conditions, we can investigate the processing of the ice as a function of these parameters in a very much controlled and more systematic way than was ever before possible. One thing that we tried was methanol irradiation. We know that irradiating methanol, you form lots of things, and indeed that's what we saw. But the thing that we could now compare is like same projectile, so protons, say protons at different energies, and it shows similar results for the destruction of methanol and the formation of other species. And we can compare that with other different projectiles, such as, for instance, sulfur. And seeing that the destruction is quite similar, but the formation of other species is slightly different, perhaps faster in the formation as well as the destruction. So perhaps the projectile matters. And the thing that you see here in orange is basically the 5% left over that is not methanol that survived the irradiation, but is actually methanol that was deposited on the back. So the substrate, the way we have it, is such that we have a hole at the back with basically a tube that will minimize the deposition at the back. Because we do deposition as a background, we will deposit everywhere around. And if we would not have that, we would have deposited 50% and 50%. But with this technique, we can actually reduce that to 5% and have just a small deposition on the back that doesn't do anything to our experiments and their interpretation. We also have an electron gun that we can use, and so we can compare electron irradiation to ion irradiation, the formation of secondary electrons in both cases, and we see we can do that systematically. We can look at the irradiation of the same ice, methanol, but deposited at different temperature, therefore the irradiation of crystalline ice versus amorphous ice, and seeing the efficiency in the destruction of methanol. And you can see that the crystalline ice doesn't destroy itself as easily as the amorphous one. And the same is for the formation of other species. When you have an amorphous ice, you tend to form more species, not in numbers, but in abundance, versus where you have the ice that is crystalline. So this is something to keep in mind when you do modeling and you look at your conditions in space, whether you have an ice that has been thermally processed or not. That is something that that should be considered as well. As well as another thing, that when you expose ices to energetic processing, such as electrons here, and you do that with different, same ice, so water ice deposited at different temperatures, so you look at different structure of the ice, the end product is always an ice that is more amorphous-like. So the dashed lines that you see here are the spectra after irradiation, and regardless whether the ice was fully crystalline or not, the end product is always an amorphous ice. So we have infrared photons that induce crystallinity or crystallinity-like effect. And then we have ions and we have electrons that induce the ice to turn back into an amorphous material. So we all need to consider all the physical conditions that and the outcome of these experiments to understand the environment we are working with. And here we also looked at CO2. and we deposit it at different temperature, 25, 30, 40, 50 Kelvin, to look at when the crystallization kicks in thermally, just by looking at the thermal spectra, so spectra of ices that were overall heated up thermally. And again, we confirm the fact that already there are not many spectral changes of the ice when we were depositing the ice at 40 Kelvin. So the ice seems to be really amorphous only when it's deposited at lower temperature, lower than 30 Kelvin. And so that is something to keep in mind. And when we irradiate CO2 ice, we, as you can see on this panel here, we form back CO, we form CO3, we also form ozone. In this study here, we looked at the formation of ozone, that is, and the efficiency of the ozone formation when it's formed by the irradiation, electron irradiation of CO2 or O2 containing ices. And we saw that the formation of ozone peaks when you have pure O2 and is the lowest when you have pure CO2. And if you think, okay, I have two ices that both form ozone. If you put them together, I should form more ozone. That is actually not the case. What we see here is that the spectral profile changes drastically. So the environment also changes the profile of the absorptions of ozone, going from pure CO2 to pure O2. And also the column density, the amount that you form is different. So in pure CO2, you form very little. In pure O2, you form a lot. And when you have 1-to-1, it's not in between. It's not exactly half of it, but it's less. So when we look at the efficiency, we saw that the efficiency of ozone formation drastically drops as soon as you put some impurity in the O2 ice. And that's perhaps one of the reasons why O3 is not well observed in the interstellar ices. But one reason is because its band absorbs very close to methanol. And so it's a little bit confused there. But the other thing is probably because if we have O3, it's formed through CO2 or O2 mixed in other ices. We don't know how much O2 we have in interstellar ices. We probably have some, but also O2 and O3 can easily hydrogenate it to form water. So either is not efficiently formed and gets easily destroyed as well. So the other chamber that we have at Atomki is to study the solar wind effects, and it's a very similar chamber than the one that I showed you before. These are just some nice pictures of the chamber. I'll just go a bit quickly because I know that I'm running out of time. And we again tried methanol irradiation, and we saw those are the first spectra that we acquired. So it's up and running now, and we can look at lower energies, but we can do positive ions, we can do negative ions there. So we can do molecular ions. So there is some scope to use this chamber if you want to study the effect of the solar wind to the solar system ices. And the last experiments I want to mention today is what I actually am doing here at Aarhus University. And I've actually been coming here since 2015 to do experimental synchrotron that is here. We were used to bring a chamber from the Open University, and that is a vacuum chamber just like the others. It's just a little bit more compact, as you can see in this picture here. And here we can use the synchrotron to do VUV, so vacuum ultraviolet, or UVV spectroscopy of ices. Again, we have an electron gun, and we can do this sort of UV spectroscopy here at Astrid in the Aarhus University in Denmark. But we also did the same experiments, repeated the same experiments in the UK at the Open University with the infrared spectrometer. So basically, we were extending our spectral range from the infrared to the UV. And the reason why we want to have UV spectra is not only just because it's nice to have those spectra, but also because observation in the solar system are mostly of ices, are mostly in the UVVs. And another important thing is that photolysis of ices have been investigated for many decades in the laboratories. One thing that maybe was underseen a little bit of underestimated was the profile of the lamps, the UV lamps that were used in the labs. They have a specific emission profile. They have a molecular emission and a Lyman alpha emission that, yes, resemble a little bit the solar emission here in gray, but it is very condition dependent. And so each lamp has a different emission. So one important thing that every lab should know is that their exact emission spectrum from their lamps before they interpret their results. The other thing is that to know the absorption spectra of the molecules that they are studying. As you can see here, different spectra have different absorption in the UV and the VUV. So say you have methane and you irradiate with a lamp that has mostly molecular emission, you irradiate in a place here where there is no absorption. So you probably will not see much happening. But if your lamp has mostly Lyman alpha, which is here, then you will see a great result. So that is something to keep in mind, especially when you are studying photodesorption and you are studying the efficiency of these processes. You should always try to do that as a function of frequency and the absorption of the molecules that you have, which is something that has been done in Soleil very nicely, but regular laboratories don't have the capability of a synchrotron, so they cannot do this kind of experiments. Therefore, they need to keep in mind what I'm just mentioning now. And just to complete, we can also have an electron gun there, so we can irradiate these ices, and we can study the survivability of these pieces as a function of the dose of electrons that we inject. And here you have ethanolamine, the molecule that Victor recently observed, and we see that the efficient destruction of ethanolamine, we can compare it to methyl formate here on the other side, and see what we form as a product of the irradiation. And so what I'm going to do now at Aarhus, Lee told you that I just moved here, is to build a new chamber that actually will be an upgrade on the one that we keep bringing from the UK. In this case, we are going to be able to do infrared spectroscopy and other kind of processing of the ice in situ without the need to move things around. And so just to conclude, I hope that I showed you that the JWST is going to change our view of interstellar ices and help us dramatically understand the formation of molecules, especially complex organic molecules in space in the solid phase. But what we really need is also to upgrade our laboratory experiments and be very careful with the parameters that we have and we investigate, because those could be key. And one thing that we can do is to go to larger scale facilities that can have the capabilities that our normal laboratories don't have, and definitely keep an eye on extending our spectroscopic range from the vacuum ultraviolet, perhaps X-rays, to the far infrared, perhaps terahertz, in order to have a complete view of the spectroscopy of ices that will give us complementary information. And all these end stations that I've been working on are open for collaborations. So if you are interested, as I said before, please let me know. And with that, I'll thank you for your time and I welcome your questions.
Well, thank you very much, Sergio. That was a fantastic talk. I think that was super interesting. So
perhaps too many things at once, but yeah.
Lots of things. It sounds like there's a huge amount of work going on in Aarhus, of course, and sort of all through Europe, really, in this work.
Yeah,
so
definitely.
If anyone wants to ask a question, they can either raise their hand. So I can see Victor has a hand raised there. Victor, would you like to unmute yourself and ask the question?
Yeah, sure. So thank you. Can you hear me? Yeah.
Yes, I can hear you.
Yeah, thank you very much for the very nice talk, a very complete talk. And it's very nice to see how many different facilities across only in Europe that we have now regarding laboratory astrochemistry. It's amazing because if you are not in the field, you lose track of all of them. And
there is much more than what I mentioned.
Yeah.
You have one right there, the Stardust machine. That is one that you have right there. So there are so many more. Soleil, I just briefly mentioned, and they also do astrochemistry. So I was very biased when I mentioned those because that was the one that I worked with.
Yeah, indeed, I have been there in the Stardust machine, which is a wonderful facility as well.
Yes.
So I had a question regarding Lisa, that you mentioned that you can simulate shocks. And as you know, I'm very interested in the chemistry of shocks because we have our favorite source, G0693, in the galactic center, in which we have detected for the first time many different molecules, including ethanol, I mean, that you mentioned. So I would like to know what is possible, what the kind of things you can do with this machine, because it would be very interesting to know, for instance, if you have formed molecules on the surface of grains, if you are able to dissolve these species, which is what we think is happening in this molecular cloud in the galactic center, or at what level you destroy molecules as well as a function of the velocity of the shock, for instance. So can you mimic these kind of things? Can you play with parameters like shock velocity, for instance? What kind of things you can try to do?
Yes. So the experiment is not a shock tube experiment. So those you have in India, there is Bala Sivaraman working at that. There are some at Kent University in the UK, and probably others that I don't know, that actually have gas gun tubes that are actually really like doing shocks, and just with either with projectiles or with gases that they use to do the shock. In this case, I'm just simulating only the thermal part of the shock. So what happened to the energy when you inject thermal energy into your system as a function of the frequency, and you look at what that vibrational energy does to the ice. It's not the full shock. Also, when I said I simulate the cosmic rays thermal effects, I don't simulate the full thermal effect, because you probably have some also like some formation of plasma, and there are other people that can do this kind of work. I only can simulate the gentle thermal effects of those. So basically, this could be relevant to low velocity shocks. So or collisions of particles, if you will, when you are in disks and you have like coagulation of different grains with ice. There is the work from Ellen Fraser that on collisions. She actually really like with pistons pushed the two ice grains against each other, and then with the high-speed cameras was looking at what was happening, and she was seeing that from the almost pure translational energy, you had also a lot of rotational energy afterwards, but the budget of the energy was not conserved. So that means that probably there is some thermal energy that is generated that is not accounted for when you just look at the image of the even in the infrared. I guess I don't know what kind of cameras she has. I guess they are invisible cameras, but I'm not sure. I'm not involved in that experiment, so I don't know. But so there is a thermal aspect even in small, gentle, low velocity collisions that is not really well understood, and that is what we can simulate with this experiment as a nice function of frequency, basically. So see, most of these effects happen when the molecules absorb the energy. So say you have infrared radiation throughout the spectrum, but the molecules will actually do something only when they have their absorption there. So only when they can receive this energy vibrationally. And then they can restructure, they can reorient, maybe they diffuse, maybe they desorb. So that's what I can do in this facility. If you are interested in studying shocks, then I can maybe point you out to the facility that actually really like reproduce the full shock.
Okay. I will contact you. Yeah, we can discuss about it.
Yes.
Thank you very much.
You're welcome.
Okay. Do we have any other questions from the audience there?
If there is not, I can do another question regarding complex organic molecules with James Webb. So yes. you have seen that to reproduce some early results, you have to play with different ice mixtures, which
yes.
At this, of course, introduce a degeneracy
yes.
to reproduce observations. So which is a challenge to interpret the observations. We are talking so far about quite simple species.
Yes.
So what do you think is well, do we will be able to detect or to unambiguously say that complex organic molecules are in the ices with James Webb? Do you think that this degeneracy problem is going to be solved somehow, or is going to be a quite challenging thing that is going to prevent us to state clearly, okay, we have this comb here, this comb here.
Yeah, so it is going to be challenging anyways, but there are some advantages and disadvantages. So one thing that you saw with CO2, that small band that I show you, is that already shows like that is quite asymmetric, and so therefore you need to have all these different mixtures from the laboratory in order to resolve that profile. Now, as far as I know, more complex species will be in an even lower percentage in these ices. And when you have just a small fraction of those mixed with the ice, their profile is not going to be very much affected by the environment so much, because they are such a small quantities that that it is not going to be so tricky to get their profile just by using their pure spectra. And also, you will not probably need to have optical constants for this molecule. So if you just have the simple spectra, just like the LIDA lab database in Leiden you probably are going to be fine with those. And spectroscopically, you will be able to reproduce this peak. Then the other problem is the spectral confusion.
Yeah, that's what my other point.
So, yeah, that is going to be tricky. And I have an absolute answer to that. I think it's a little bit early at the moment. People are starting looking into it. And yeah, at the moment, the discussion that I'm listening to is that they want to have the data out as soon as possible in order to provide the first spectra of JWST to the community. And they also have like deadlines and obligations for that. So at the moment, they're not looking too closely to these weak bands, but just giving the overview, the overall picture, which seems to actually reproduce very well what we already know. So even at high extinctions, the relative ratios of water, CO and CO2 and so on, it's quite well preserved with what we already have observed in field stars, for instance. So it looks like nicely consistent. The picture was correct, probably. And it's a gentle and slow evolution, I guess, there at that stage. But for the complex organic species, then it's going to take a little bit longer to look into that. And I think like many people are going to start working at that, and I'm sure that a few species will be identified. Maybe not many, but at least a few key molecules that perhaps are a bit more abundant. Maybe methylformate, maybe some simple acids, maybe, we already know that we have formic acid, maybe acetic acid, some other small species. The trick is that if you are able to have species that have unique bands, and then you can identify 2 or 3 of them in the same spectrum, then you are more sure that actually that is the molecule. So we need to look into that closely and see. The problem is that all these bands are very weak, and so you could feed them with many different things, so the degeneracy that you were talking about before is going to be there. But my personal view is at the moment is that we will be able to identify some of them at least. And definitely say that we will have families of molecules there. So there is, for instance, in the red wing of water ice, a 3 micron, so 3.3 to 3.6, there is a band that is mostly attributed to methanol at the moment, but that also could be given by aliphatic species, could also be due to hydrogenated pHs, and we are looking into that. So now we are trying to reproduce the spectra and see if those will actually help the fit. And even if we get a nice fit that is better than what we have, there is not going to be like a unique probably solution to the problem, but there is a suggestion that those pieces are there. So yeah, I think that would be easy to reach that kind of level of like suggesting that these pieces will be there. You unambiguously identify single combs is going to be harder, but perhaps in few isolated cases we will succeed. And also the thing that we can do with JWST is look at spatially different line of sights. So maybe we will be able to trace, and this is something that I also do in the experiments. So when I just change conditions slightly, then I compare, then it's easier for me to see things that I might have missed, because in one experiment I might see like the formation of a species very clearly, in others was hidden within the noise of the other molecules. But now I know where the peak should be. So I'm like closely looking at that. And maybe that is the way also is going to be with JWST, that we will be able to find species because we are looking more like everywhere around in these regions than just a single observations here and there. So that's my opinion. That's my personal opinion.
Is that because of the sort of multi-object capabilities of JWST, or is that literally different kind of telescope pointings?
I think it's that I'm not an expert on the instruments of JWST, but I think there is like the possibility of having a near spec, near cam, and they have a wider range of observation. But probably Victor knows better than me that because of the instruments that you have there, you can actually, and the sensitivity that you have there, you can now actually look at ICES in absorption at different
positions. Yeah,
different positions. Yeah.
At the same time, yes.
Yeah, and you not only get an image, but you also get the spectra for each positions if you have the source on the background. So now you can see sources. You are more sensitive to sources of the background that you were before. So you have more options and more line of sight that you can see.
Oh, fantastic!
I mean, that's my simple understanding. Of course, I'm not an expert on that.
Yeah. Well, thank you very much, Sergio. That has been extremely interesting for me as a kind of outsider from the astrochemistry kind of field, and it's obviously been extremely interesting for the sort of the experts here at the CAB as well. So thank you very much, Sergio, and it's been a pleasure to have you with us today, and we hope to see you at some point in the CAB, I'm sure, soon.
I would love to come visit. Yes, definitely. And thank you so much for the invitation. And yeah, I might come for beam time at the Stardust machine. So, and if I'm around, I will definitely pop in and introduce myself.
Sure. Let me know. Let me know if you come.
Absolutely.
Bye.
Okay,
bye,
so
Sergio. Thank you.
Let's thank Sergio again, and yeah, fantastic. Thanks, Sergio.
All the best.
Bye.
Bye. Bye.
Okay.